we introduce this symbol. It's a circle with a plus sign in it, and we call that exclusion. Prove the exclusion law, and then we're going to have an example for the exclusion and how we solve for it. Proving this, it says P exclusion or Q, which is logically equivalent to P or Q in the parentheses and negation or is not P and Q. And so this is read this way. It says P or Q but not. So in this case for the exclusion it's read but and, right? And so that's what the and means. It says P or Q but not this, right? So just a transition to telling you the other part of the statement that needs to be satisfied. And so this is what we're trying to prove. So I hope you understood what's happening, what's going on. And so now we create a truth table. And so our truth table, the first thing we need to do is put our statement variables, which can be P and Q. And then we got to put on our compound statements and what's going to be at the end of our sentence. So it's P or Q is right here, right? So I'm going to highlight it, P or Q. And in orange is we're going to have P and Q, which is going to be right here. And then we want the whole thing with the negation, or is not. So we want that with the plus negation here, you can see that. So we want all that. And then finally, we're going to have our whole statement, which is just the whole blue highlighted, right? Everything highlighted in blue. And the last thing to mention is that you don't need the logical equivalent sign right there. I only have it there to show you that this is the end of our sentence. And these are all compound statements, right? Because of these little ands and ors. But those little ands and ors and is nots form the compound statements. And so with that being said, let's carry on with our proof. And so what's the first thing we need to do? We need to put on examine our truth values. And so the first thing we do, we go true, true, false, false. So first two is true, next two is false. Then it's going to go true, false, true, false. Alright, so now we have a P or Q. So with the statement of P or Q, one or the other has to be true or false. And so, as we can see right here, these first three are true. And so I'm going to put a little dots right here. So that's true, this is true, that's true, and this is true. And so that makes our statement, if you could tell, true, 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 and the last two are false. And so we have a P and Q. And so what do we need this statement to be? Well, we need this statement to be true for both its parts of the statement. So this is the compound statement, and we need both the parts of our singular statement to be true for the compound statement. And so right here you could clearly see that there's a false and a false, two false down here. So it's going to be true, and the rest are going to be false. And so we're going to put that down there. False, false, and false. And now we have the negation of P and Q. So where do we look at for the negation P and Q? Well, you just simply look at this, and you look at this, right? And you can see this is P and Q, this whole entire compound statement. And so we're just trying to negate that, right? We're trying to have the is not of that. So it's just going to be the opposite of the truth value for that. So it'll be false, true, true, and true. So now we finish our statement variables / components and finding the truth value for our compound statements. So the last thing we need to do is put that into our sentence. And so right here we have our whole entire sentence. It says P or Q. So now we have P or Q, and, or we could read it as but, because that's how you're supposed to read it. P or Q, but not P and Q. So that's where we're going at right now. So let's go right here. We have P or Q, and so what do we have to look at? And so let me highlight this with a certain color. So we're looking at P or Q. So we're going to look at this, P or Q. And what else are we looking at? We're going to look at, so I'll use this color. Well, actually I'll use another color. I'll use this color. And we're looking at this. It's just going to be in gray. That's what we're looking at. Alright, so they both have to be true or the whole entire statement's false. And so you can clearly see that this statement is going to be false, right? Because this is false. And then you can see a false right here, so you know the first row and the last row are going to be false. And so we're going to have to write that out, right? We got to write out false, true, true, because you got to have both the compound statements to be true. And so bring that down a little. And so that's going to be logically equivalent to. So I'm going to write this just for the sake of you understanding what's going on. And so it's going to be logically equivalent to P exclusive Q. And so these three little signs means logically equivalent to. So it's logically equivalent to. And so it's going to have the same truth value. And so that's what we denote this symbolically. So that equals this. Or you could say logically equivalent. So now we understand this proof. So this sign, these three little signs, they mean conclusion or therefore. Therefore is the formal way of stating this. So I'll bring an arrow over here. So this sign means therefore. And so this is the first time you might be exposed to this. So that's what that sign means. And so we use that sign for therefore. And then we go over here. So I'm going to draw this a line right there, separating this, what we're going to do right now. And then you bring that down. So therefore, our exclusion for P and Q for the statement is true, right? That's basically the same. So I'll read it out for you guys, for everybody, so you can understand what's going on. It says, P or Q, but not P and Q, is logically equivalent to P, right here, P, exclusion Q. So, or read it one more time. P or Q and negation, or is not, but negation, P and Q, is logically equivalent to P is not Q. And so that will be our proof. You say, you put these three little signs, you bring this down, and you say that, or you could write out other stuff. And so the whole point of this class is getting used to phrasing things in a way that's easy and getting better at it. And so right now, this is probably the most efficient way. You just write the three dots and then bring that down, and that's all you need to do. And depending on your professor, they're going to probably tell you what to do and what else to mention for this. The last thing I wanted to mention is you're going to hear me interchange words a lot of times. And so this is the formal way, right, for saying therefore. A lot of times I always say thus, and all that really means is we're concluding the statement. And so you could interchange words a lot. And so the same reason why we interchange but and for this word, and the same reason why we interchange negation and is not for this word. And so what I really want you to get out of this is to know that there's multiple ways of saying something. There's a more formal way in mathematics to say it, and then there's a more informal way in mathematics to say it. And so just keep that in mind. And so now we're going to come down here and we're going to do an example to finish off our video. And this example has to do with the exclusion. And so we just proved the exclusion. And so let's go down here. And it's all it's asking is to find P exclusion P, and then find the statement of P exclusion P and the exclusion of P again. And so this might take a little longer than anticipated, because if these are, it's not expecting you to know what to do. It expects you to know that this means this, but that's for P and Q. What happens if you have a P and P? What will the truth value be? So you were forced to having to know this kind of formula or sentence, right? We should say sentence is better, because that's what we're learning, logical sentences and statements. So we gotta put down our whole entire thing again. This time, instead of being Q, right, we're gonna have P or equal to. And so that's the whole point. If you could find the proof for something, you could work out any example. And so if you haven't already, we're going to take a look at this. And so we have P or P. And so we're taking a look at two P's. And so I'll write one more P. You don't have to. Right, the truth table is kind of, you can skip steps if you want to, depending on if they want you to show all your work, but you can skip steps. And this is one of those steps you don't necessarily need. You don't have to write out the extra P, but if you wanted to clearly see what's happening. So we're looking at P or P. And so it's going to be true, and then that's going to be false, because two false doesn't make a true for a given OR statement. What will the... Oh, let me check if I did this right. Yeah, it's going to be negation P and P. So this seems like it gives us a false and a true. And so these kind of things you can make a mistake, so be careful. So we have P or P. So now we gotta look at everything and evaluate it for what it has to offer for us. And so what do we have to look at? So I'll use a different color just so you can see. We're looking at P or P, which is gonna be right here. And then we're gonna look at this statement right here. And we're seeing if both the truth values, which is the T and F, if they're both true. And so it seems like they're both false. So we have two false statements. And so we could conclude that this is going to be false and false too. And this is what we, two P's, right? For two statement variables that are P. And we're given, I'll write that over here too, just in case you don't know. This is where we're trying to find the exclusive. And that's going to be OR, right? I'm trying to find the exclusive OR. And that's an OR in cursive. So. Alright, so now we're going to get ready to start our, finish our example. And so you can see this example is a little longer than what you would want it to be. So it's just might not be on a test, depending on how long your test will be. So it's going to be a true or false, right? Because you're given a P. And so what we're trying to do, we're trying to find this now. So we found this first, so we already found that. So we got the answer, right? And now we're trying to find this. So we know what the truth value is for P and P, but now we want to know what the truth value for this given P is. And so for this, we're going to get ourselves used to doing this. So in mathematics, we do this a lot. We say let something be something. And so we're going to be right here, so I'll put it over here, a little farther away though. So just know this is what we're working with. So we're going to say let P exclusion, the symbol, right? P be A, or equal to A. Maybe sound a little better. And so now we we transformed our big lengthy compound statement into just NA false. So we got 2 falses, and now we gotta carry on. So what do we need to do now? What's the next step? Well, we gotta do what we did up here again. It's just the same process. But basically you're gonna write out the whole entire thing again. And so we're gonna go A is gonna be A or P. So let me put this right here. Yeah. So now we're gonna work out, we found our statement variables, and now we want to find our compound statements for this again. And so why are we putting A first? Because A is obviously first right here. And then we have our P. A and P. And we're gonna find out that's gonna be logically equivalent to this statement. P and exclusion P and exclusion P again. And if you don't know where that's coming from, I'll put it out on top, and I'll put it in this color. Remember where we said that be A, so this is what we're finding. Same thing. These are all going to be logically equivalent to each other. Just denote it into different symbolic language. And so here it's going to be A or P. So we're going to have true or false, and so we obviously know this is true, this is going to be false. We got A and P statement, so this is going to be false and false. Because why? Because they both have to be true. In order for the statement to be true, this is going to be the opposite of this, so it's going to be true and true. And if you don't know, I hope what do you call it, go watch my other videos and maybe you understand those ones. And I'll explain it slightly right here. So when you do the negation of something, right, that's going to be the opposite of the statement that's being said right here. So this is the statement being said, and it's going to be the opposite of this statement. So it's going to have opposite truth values. And so right here we have A or P, and negation A and P. And so what do we have to do? Well, if you remember what we did on top, then that's exactly what we got to do. So we got to look at the two things again. So I'll highlight a certain color so you can clearly see what I'm doing. That's kind of messy, huh? So right here we're going to have A or P. And so what does it have to be in order for this to be true? It has to be both true. And so we could clearly see this is true, this is true, so therefore that's going to be true. And this is false, and so, right, I'll put it in a yellow color. This is false, so it has to be false. And so right here we have true and false, and so that has to be logically equivalent to this and this. And so therefore this has to be true and false. And so what do we see? And so if you remember, when we are doing the logical equivalencies, we always want to take note of the little truth values that everything has. So these are logically equivalent, but what else is logically equivalent? And so if you come all the way back over here to this P, you're going to see that P is logically equivalent to this whole entire statement. So we didn't have to do all this extra stuff which was inside of it, because all it meant was the same statement P. And if we denote our statement variable with a certain word, right? We say John is running. We didn't have to say all of this. We could have just said John is running. So this is saying John is running, doing something else, doing something else, doing something else, but then he's doing this and then doing that. And so if you don't want something that complicated. But that's besides the point. This is we've shown these two examples and we proved that what P and P was right here, so we did that. we showed the proof. So we did that too. And then we show the answer for this. And so what's the last thing we need to do? Like I said, we gotta say that thus this is logically equivalent to that. And so we prove right here, so I'll put it right here. We prove thus or therefore. Therefore is more formal, so I'll try to say therefore more often for you guys, for everybody, so you don't get confused. So therefore P exclusion Q, and we prove that. That too, just in case you're confused, that should be P. I'm not sure if I did it wrong earlier in the video, but that shouldn't be P. And so finally, we say P exclusion P. And so I'm writing this out because it's logically equivalent to a lot of stuff. P, and that's logically equivalent to, and then you could write this statement, and you put that down there. Down there, see that? And so we don't have to put this because we changed that, right? So I mean, you can put it if you want to, right? You could say, oh, that's also logically equivalent to saying this. So it all just means the same thing. But you don't really have to. Right, we wanted to see was this. And so I put it in red. All we really wanted to see was this and that. And this too. Not as much, but it's good to point it out. So that's going to be our answer. And so that's going to be it for the video. If you enjoyed this video, please like the video and please subscribe to the channel. It helps a lot for helping my channel grow. And if you want to see more videos like this,